Hi, welcome to my talk on building a new tail calling interpreter for Python. But this title actually isn't 100% correct because it should be measuring the performance of compilers and interpreters is really hard. Yeah, so I mean, I'm not as famous as Pablo, so I'm just going to introduce myself. Yeah, I'm a core developer since August 2021, and I worked on the specializing interpreter with Mark in 3.11 and Brent and a few other people. And I implemented the JIT's initial optimizer at the start of the JIT project, but we're still working on it, so yeah. Yeah, so for those people, I mean, you've been hearing like CPython, CPython, CPython throughout this whole conference, and sometimes you need to ask yourself, like, what is actually a CPython? So Python is a programming language, like everyone here knows what Python is. Well, CPython is the reference implementation of the language. In other words, it's Python implemented in C and compiled to a binary, so like an exe file, in your computer. So it runs on your system as an actual executable. So back in 2022 in EuroPython, this really charming gentleman said, had a bunch of pretty diagrams on the screen and said, okay, yeah, we're speeding Python up. And yeah, we want to speed Python up. And I'm not going to play it here. You can watch it online. But you want to speed up Python, right? And we need to do some profiling. So we profiled, and this thanks to Mike Dropboop. So we profiled a set of benchmarks in Python to see where time is being spent in. And I'll just zoom in a bit. So each line, horizontal line, is actually a single benchmark in our benchmark runner. And if you look closely, it says the interpreter is roughly 30% of the time on average of the total in all the benchmarks. So let's speed up the interpreter, right? Like, yeah, we can just speed it up and we'll get like, if we speed it up infinitely, we get 30% faster. And yeah, we need to understand the interpreter first before that. So a few talks ago, or yesterday, they actually clarified that Python source code is compiled to bytecode, which runs on an interpreter. And bytecode is basically just simple instructions that you run on a virtual machine. That sounds very like pie in the sky kind of thing. So I'll explain like with a simple example. So if you have x plus x in Python, it compiles down to load x, and add x together. So it's pretty simple what they do. But you basically have a stack, this data structure and the interpreter. And it puts x onto the stack for load fast x, load x again, and then add them together and put them back on the result onto the stack. So now you are all experts in how Python works. We now know how to do, we now want to see how these are actually implemented in Python itself. So the traditional interpreter in Python is actually a switch case. I mean, not in Python, but back in the day, like really when maybe Guido first started this project. So it was a switch case, and basically it says, switch case instruction 1 and then case instruction 2, and then you just break. So this is simple C code. The problem with the switch case is that in a naive compiler, you have 2 jumps per instruction. And you have 1 jump at the top, but the jump is like a mega jump. It jumps to like so many different instructions. So on older CPUs, the folk law is that this is not that good. But on newer processors, this actually doesn't matter at all. Or mostly it's completely eliminated. But we still care about older processors sometimes. So let's abuse gotos, and this actually by Antoine. I think he implemented it in 2011 in CPython. And the current interpreter is implemented using gotos in Python. So I'll walk you through the example, and I'll do it slowly because apparently I forgot to start a timer, and I don't know how much time I have left. Yeah, so the interpreter is actually, you have a dispatch table, and you put the labels of what you actually want to jump to in the dispatch table. And each label corresponds to the actual instruction that is executed in Python. So at the start of it, you have a goto to the dispatch table. Okay, so just to run you through a simple example. At the start, it says go to, then dispatch table instruction pointer. So this means go to the next instruction. So let's say the next instruction is instruction 2. we execute instruction 2 and its subroutines, and it says go to the next instruction again, and let's say the next instruction is instruction 1, and so on and so forth. So as you can sort of see, it's actually slightly more efficient than the previous interpreter. It's, in a naive compiler, it's 1 jump per instruction. And the branch targets are spread across multiple jumps. So the folklore, again, is that this is better for branch predictors in older CPUs. But again, it's not really the case in newer CPUs. So here's the problem with the goto interpreter. We have no direct control over what we want to put in the machine registers. You just trust the register allocator. The register allocator is the thing in the compiler that says, okay, I put these things in registers, and registers are ultra-fast pieces of memory. So the compiler, you just trust the C compiler to say, okay, I want this thing in the register, and there are ways to put it manually into register using inline assembly, but we don't write inline assembly anymore in Python because it's unmaintainable, and Python runs on so many different platforms. Another problem is that the old interpreter is massive. It's over 12,000 lines of C code in Python 3.15 now. So it's prone to so many compiler bugs, and I'm not even going to go through them. I'm just giving a list of the ones that I know of. So there are more than that. And it's too complicated, basically. The interpreter is too big. We hit magic thresholds in the compiler, and that causes problems. So here's an example, and I don't need you to read the assembly. Just look at how it looks. So that's vibe code it, vibe assembly. So if you vibe assembly it, on the left is actually a buggy dispatch body. So the dispatch is basically the thing that at the end of the instruction that says what's the next instruction to go to. And if we look at the assembly, it's actually 2 jumps and a bunch of register shuffles to get to the actual next instruction. But on the right, it's actually just a single jump, and the register moves are almost as good as we can get. And it's actually observed by Matt Page in one of the bugs that we caught in CPython 3.14. So, and the previous bug actually caused about a 6 or 7% performance regression in Python. So it's pretty significant. So we need to ask ourselves, can we do better? And this clearly is someone else's tagline. So there's this concept of tail calls in programming languages. A tail call is basically a call in the last position of a function. So if you have, for example, func x, and you tail call into func x minus 1, since it's in the last position of the function, it's a tail call. And in 1977, Guy Steele published a paper that says tail calls are equivalent to gotos in most scenarios. So the idea here is to implement the interpreter using tail calls and not gotos. And this is credits to a bunch of other researchers and contributors. So again, I'll show a demonstration of the difference between the interpreters. On the goto interpreter, you have one function, so one massive function, 12,000 lines of code. In the tail call interpreter, you have 225 smaller functions, up to 200 lines of code each. And how we implement it is that we have a proper tail call attribute that says, this must be a tail call, otherwise you fail compilation. So we don't even let you compile the code if it doesn't compile into a tail call in C. And we have this special calling convention that forces important parameters to always be in registers. So we know exactly what we want to put into registers at the start of the function and at the end of the function. So it gives us more control over the registers that we want. So this is actually the code change, the actual code change in Python that we had. So if you look at it, it's not that much. It's just a single if-def in C, and an if-def in C is just a thing that guards compilation. So it's just a single if-def. And how we achieve this is that these 2 macros in C actually boil down to different things in different compilers. Different interpreters. So in the goto interpreter, it becomes a label and a jump, like you saw earlier. And in the tail call interpreter, it becomes a function header or function prototype and a return statement. So this is where it gets fun, the initial performance results. At first, it was over 15% geometric mean speed up on some platforms. So I was like, wow. And for 4 weeks, I was like this, like I was like jumping for joy, you know, and going around and like telling people about it. But and it was merged into Python 3.14, so yeah, that was nice. But obviously, as the title of this talk suggests, like the real title of this talk suggests, that compilers, measuring the performance of compilers and interpreters is really, really hard. The cake was a lie, and it still is a lie. So it was too good to be true. Another contributor, Nelson LH, spent a month doing excellent investigative work, and he really had to dig really, really deep on why this was happening. But there's this great blog post, and the short summary is that, okay, I was really sad, but the short summary is that, the computed goto baseline interpreter had a bug in the C compiler. Yeah, who would have expected that? Like, wow, the 12,009 function has a bug in it. Yeah, and what happened exactly? So this isn't the actual assembly, but this is just roughly what happened. The interpreter on the left is what we want it to actually compile down to, like what it should behave like in a real world scenario. The interpreter on the right is actually what the C compiler effectively compiled it to. So basically it compiled it to a bunch of, it deduplicated the jumps at the end of the interpreter, or the dispatch body at the end of the interpreter, and made it into a single common jump at the end. And that's basically undoing the whole optimization in the first place, because now you have an additional jump, and it's going to like register shuffle and a bunch of random stuff. So yeah, there's 2 jumps now to the next instruction. It goes to a common jump, and then it goes to the real jump. So in other words, the performance results were good because the computer goto interpreter got slower due to a bug, but not that we got that much faster. And so here are the real performance results. And if you look carefully, on x86-64 on Linux, there is a small speed up, and we do measure it, so it's around 1.5 to 2%. On Mac OS, there's a 5 to 7% speed up, but the thing is, we think the Mac OS compiler has the same bug, but we're not too sure because there is another bug that interferes with this bug. So and the bug is due to profile-guided optimization. So that's the thing that helps the compiler like optimize based on runtime information. So there's this other bug that that forces us to not be able to measure it properly. So yeah, this whole thing is just a bunch of bugs. And on x86-64 on Windows Clang CL, which is unsupported by the way, we don't actually build any Pythons with it. It's just for fun. It's supposedly a regression. And yeah, the TLDR is that performance gain is not as good as we expected. So yeah, I was like, oh, okay, yeah, sad for like 1 week. But like you might ask, like, so we need to start investigating. Why is there no speed up? Like this thing promised us to be faster, and it's not that big of a speed up. And the thing is, the compiler can probably outsmart us, even in the case of normal computer goto. So that's the goto interpreter. And there's some side benefits, however. So it's not like I'm here to whine about the interpreter and like the performance of it for like 20 minutes. But the interesting thing is that out of this, we actually got support for Clang on Windows. So that's actually a pretty big improvement, because previously we couldn't even build Python 3.14 with Clang due to some strange compiler differences between Clang and MSVC. And that's MSVC is the Microsoft C compiler. And we added Clang support to it. So this thanks actually to Chris Eibel, like another contributor in CPython. And there are actually more sanitizers available now. So sanitizers are just like things that help to detect thread problems or memory unsafe stuff in C. And we actually added, now that we have Clang on Windows, we can actually run sanitizers on Python. So it's actually a great thing because a lot of the Windows code was Windows specific, and we couldn't even run any sort of like tools on them because like maybe sometimes MSVC might not have the tool that we want. And we refactored the interpreter in the process of doing this as well. So we actually push more things into a domain-specific language that we are using, and that actually helps to ensure the correctness of the interpreter rather than just trust the C compiler to do it for us. We also caught multiple compiler bugs in Clang and GCC. And this involves lots of special attributes which affected multiple projects. So like, for example, in Clang, you saw that the bug that was affecting the computed gotos and deduplicating them was actually found in Clang 19 and affected Loa U as well. That's the Loa dialect that they use in Roblox, I think. And GCC also is trying to implement the special calling convention now, but they do encounter some bugs, so we're helping them fix it and run tests for it. And finally, well, not finally, but another side benefit is that we get a more resilient interpreter. So the new interpreter might just be slightly faster on some platforms, but the thing is, tail calls have been around forever. Like you saw, like I said, tail calls. The paper was published in 1977. So optimizing compilers have been doing tail call optimization for a really long time. And right now, we are relying on tail call optimization rather than computed gotos. And computed gotos are basically a compiler extension. So they are not actually part of a standard compiler. So that's why I suspect that most of the time, the computed gotos get hit with bugs, but the tail calls don't get hit with that many bugs, because the tail calls are essential optimization, and the computed gotos is just this one specific extension that only interpreters use, and it might not be as well tested. And here's the really cool thing, we have better debuggability as well. So profiling can actually now see CPython bytecode, because when you run perf profile on CPython, it's now each of the bytecode is a single function. So we can actually see how much time is spent in each instruction, and this actually helps us improve our future performance improvement efforts, because now we know, okay, this instruction is slow, we might need to speed it up or investigate it. And this, again, thanks to Mike from Microsoft, who, from the faster CPython team, who worked on this. And there's also actually better JIT performance in the future with the tail calling interpreter as well. So right now, the JIT actually has to call, one of the reasons why the JIT, switching from the JIT and the interpreter is slow, like there's some overhead, is that the JIT has a different calling convention than the interpreter. So when the interpreter calls to the JIT, it needs to change the calling convention. And that's slow, because you need to reshuffle your registers and everything. But in our near future, and I already have a working prototype for this, it will call from the interpreter straight to the JIT machine code, and the JIT machine code will tail call back to the interpreter. So it will just be a single jump from the JIT to the interpreter, and a single jump back from the interpreter to the JIT. And that's a huge improvement in the JIT. We might not measure it yet, but we switch JITs from compiled code to an interpreter really often due to the architecture that we use, which is called tracing. I think it was covered on the first day. But tracing JITs basically switch between tiers really often. So having a faster calling convention, a faster way to switch between them, is actually a huge benefit for the JIT. There's also slightly faster build times. I say there's 3 to 4% savings, but this is like out of a few minutes of compilation. So that's actually a pretty big win. And the fact that this is just a single file, like all we did was modify a single file and we got 3 to 4% savings is also pretty nice in my opinion. But I need to add some disclaimer just so that I don't get sued. So the performance results are for Clang. I have not yet benchmarked GCC 16. From what I tested, GCC 16 actually regresses the performance of tail calls a little bit if with profile guided optimization turned on. So that's a bit strange, but I think it's a bug that we can probably fix. I mean, all the GCC developers can help us fix, hopefully. And in the toy benchmark on a BF interpreter by Brandt, the tail call outperforms the goto in a GCC 16 compiler. So, but I can't extrapolate the results here, but I just know that it actually outperforms it when I tested it on my system. So I want to actually thank quite a few people because I don't like the notion that, okay, this person actually did it on their own, so yeah, I'm responsible for it. I mean, okay, I am responsible for the slowdown and the other stuff, but a lot of people help me for this. Like, they help me either debug stuff, profile stuff, because, for example, I don't have a MacBook or an ARM laptop, so I had to get help from the people who have ARM laptops to help me with it. And a lot of people helped me with this project, so I'm really happy, and thanks to everyone who helped me on it. And the next thing I want to advertise is that there is a EuroPython open space happening on Friday 2 to 3 p.m. where we'll talk about the JIT. So far, we have confirmed that the CPython JIT compiler developers, some of them, possibly more, will be there. And we have PyPy and GroundPy people that we've invited, so they're probably coming, hopefully. So yeah, we hopefully will see you there as well. Like, we want to talk about JIT compilation or interpreters in EuroPython, and I think it'll be a great venue to talk about it. So the key takeaways from this talk is that measuring performance is really hard. You shouldn't trust the compiler, but you should also trust the compiler. Yeah, okay. Yeah, that's basically it. Thanks for listening to the talk. You can email me. Yeah.
Right, thank you. Since we are perfectly on time, does anyone has any questions? And if yes, please feel free to come to the mics and ask them.
Hi, quick question. I'm not super familiar with this, so it might be a misunderstanding, but you said when you had the slide on about the, debugging the performance, that you now can see the bytecode effectively in the performance measures. I don't think I quite understand it because you said if it's a tail call, it should be inlined, right? So then it shouldn't appear as a function because the whole point is to not create a stack frame for it. So how does it appear?
Okay, so that's a good question. I think if you compile with frame pointers, and I'm not 100% sure because I didn't do the profiling, you should still be able to see the tail, like how much time is spent in each bytecode as a function. Like, I don't think it's completely inline. There's some probably magic tricks going on in Perf. But I'm not 100% sure, so I can't answer that, sorry.
Okay.
Yeah, thank you. Thanks for the question.
Hey, thanks for the great talk. My question is, you mentioned that it's now introduced the tail call interpreter in Python 3.14. And my question is rather, is it now fully replacing the goto interpreter in that version already, or is it like experimental for now? Will it become the standard in the future? Are there plans for this?
It's not experimental, so you can actually build with it. We don't have experimental tag on it, but we don't want to replace the goto completely because some compilers will need to support that for years, and we need to support older compilers as well. This feature is only available on newer compilers, specifically Clang 19 and GCC 16, which is like just released in the last 2 years or so. So we need to keep the goto interpreter around for basically forever. Yeah, because I mean, or at least have like a 10-year cycle or something. And by then, I hopefully will be working on something else. So, so yeah, but we basically need to support both forever, but we basically say if you want to build a newer compiler and you want to build with the JIT, we'll provide better performance with the tail call interpreter. So yeah.
Okay, thank you.
Thanks for the question.
All right, we still have time for 1 or 2 short questions, if anyone has any.
So you just said we got to keep both around. Does the makefile right now or configure automatically detect if you can use it and automatically select it, or you still have to opt in?
You still have to opt in because we found that for some reason instrumentation on the tail call interpreter is broken on Clang. Yeah, so we are not too sure why. Like, but okay, so I can give some context. Like, I know a big Django monolith that is using this feature right now. If you know, you know. So they actually found that there were some problems with instrumentation, like with tsend and everything. So yeah. Okay.
What is it about the tail call version that's more optimal than the goto version?
Sorry, you said more robust, right?
More optimal.
More optimal. Okay, so I mean, if I go back to one of my previous slides, there's a few problems with the goto interpreter. So I said like there's no direct control on what to put in machine registers because in not so good compilers, they actually spill over everything because the goto is so huge and the control flow graph is so complex. So they just spill registers everywhere and put it into the stack, which is slower than the register. Another thing is that it's just like so big that some compilers don't optimize it very well. Yeah.
Oh, thanks.
Okay.
I have a question. I had a discussion with colleagues and we didn't quite understand. The 3% or 4% advantage, like speed up, was speed up of building the compiler or actually compiling Python code, like execution time?
Oh, the 3 to 4% like speed up. You mean like the build times speed up, right? Not the performance speed ups. Okay, so this is for running Python code. This is for high performance. And the speed up, the build time speed up is for building the Python C, like building the C compiler itself, not compiling Python bytecode.
Okay, so compiling Python bytecode is speed up?
No.
Okay.
Sorry. Yeah. Okay. Thanks.
Thanks.
All right, if anyone has any more questions, we still do have time. Yeah?
Thanks for the talk. I have maybe a crazy question. Were there any efforts or ideas to just sequentially execute tuples or triples of the instructions and then go to next triple? I know it would be like power or expansion of the set of the instructions, but like, would it be possible?
Wait, so you're suggesting like to execute 2 instructions in one shot, and then, okay, yeah, so those are called super instructions. They've been around forever as well. And we actually do them in Python, but only for select few. Because so the idea in Python is that the dispatch overhead is actually not as high as the actual work being done in the interpreter itself. Like Python bytecode, each bytecode actually does a lot of work. Like load an attribute, for example. I mean, you saw in Antonio's talk, it does a whole bunch of crazy stuff. So it's not, super instructions don't actually gain us that much, basically.
I see, thanks.
All right, thank you all for the questions. If anyone has any more, we can facilitate one more, I believe. But if we've satisfied your curiosity, then once again, thank you so much for the presentation.
Thank you.